In the previous lectures, we talked about the learning problem. The purpose of learning problem is we have a historical data set and we apply an algorithm. We try to find a model that tries to understand how decisions are made based on historic data. The question is, when you learn that historic data, how do we know that model could work in real life, okay, on the test data set? So that is the problem, right? So to solve this problem, so we understand that if you have a very powerful hypothesis set, it can fit to any training data. It can fit to any training data, meaning whatever training data you generate, you can always learn it. If that is the case, you cannot be sure that model will really work in real life, because that is too powerful. So it can adjust itself very well to the training set. So we need to have a hypothesis set, a model that is generalizable. So it works on the training set, it should also work on the real life. But that is the main concept in that one. What we did is, how do we determine the strength or power of a hypothesis set? So what we did is, to understand the strength or power of a hypothesis set, we pick endpoints, okay? And then we check all possible labelings of endpoints, and we check whether your hypothesis set is good enough to generate all hypotheses for all possible labelings. That's what we did, right? You pick endpoints, and if you have two classes, you have 2 to the power n combinations of all endpoints. Okay, you fix the points. You don't change the points, you just change the labels. And then based on those labels, what you do is, whether your hypothesis set has a hypothesis for each of the labelings, basically. If that's the case, we say it shatters endpoints. Okay, but it's hard to know n directly. Okay, you cannot determine what n is. N could be 1, 2, 3, 100. It could be any number. For the examples we have tried, we start with n is equal to 1. Check whether it can shatter 1 point. We went into n2, 3, 4, etc. That's the way we have that. So whenever you reach n, a number that it cannot shatter, we call this a breakpoint. At that time, we know that this hypothesis has a limit, which is a good sign. Whenever there is a breakpoint, we know that the error could be limited. We could train the system properly and limit the error for real life. Okay, that is the general idea of this BC dimension. So this is so complex. Hypothesis set or complex model doesn't mean that they are better in this context. So you need to have something simpler, but generalizable. So this is an important graph. So in this one, what you see here is you increase the model complexity. So VC dimension increases, basically. VC dimension is breakpoint minus 1. So it is the highest number of points your hypothesis set can shatter. One more cannot shatter anymore. It's called breakpoint. Okay. As the complexity, so VC dimension is related with model complexity, basically. As the VC dimension increases, you see that training error goes down. You get better training results, but error initially goes down and then goes down. So at this point, so the model that appears at this position is a better model for our analysis. So we use this a lot also for deep learning or neural networks. So you are going to see that training goes down, continuously it goes down. It can be even 0, but you need to have another data set to make sure that to observe this better position. So whenever you see this going up, you stop there, you stop your training, and then you choose that model to be your best model. So this is applicable to other areas. So there are several concepts. One of them is called overfitting. Okay, overfitting means your model fits very well to training set, but it doesn't fit well for the validation set or test set, meaning that it overfits. So a good example of this one means what I mean by overfitting. I gave this preparation for the exam. Okay, you work on the sample questions and you prepare yourself for the actual test. But what the model does is, or what you do is, rather than the learning the concept, what it is, you just memorize it. Okay? Memorize it. So if I ask the same question as in the preparation sample test, you get 100. You work perfectly. But if I change the question a little bit in the numbers, you cannot, if you cannot solve it, then what you do is you overfit yourself to the sample questions. Okay, you cannot generalize something new. But that's called overfitting. So we say that I'm going to put it that way. The model that you build memorizes the data. It didn't learn it. It just memorized what the data is. It works very well, but it doesn't know what to do when it sees a new data set. But that's called overfitting. Okay, that is one case. Typically, how do you understand? When you measure training accuracy and test accuracy, you are going to see a big gap. Training is very high accuracy, but test accuracy is very low. Okay. There is something called underfitting. This is also possible, and there are several reasons for this. But one reason is sometimes the model that you pick, hypothesis set you pick, is too simple. Okay, for example, the actual class is represented with a circle. Okay, I'm just giving you the actual class, for example, that plus examples. Okay, it's an area line, it's represented circle. Rectangle is also close enough to circle, it may work. But if you use a line could be too simple. It cannot capture most of the information over there. So you're not going to get good results even on training set. Okay, even on training performance will be very low. So that's going to be typically called underfitting. So it means that your hypothesis set, the model that you choose, perceptual model, was not good enough for that domain. You need to pick something more powerful. Okay. So these are from the old information, but let's try to remember these estimators. That's the estimation. Histogram definition, what it looks at is you look at basically, you fix the interval first. For example, you said interval is 0 to 3, or your interval length is 3, or you said, let's say your interval length is 5. You check a number of samples in 0 to 5, 5 to 10, 10 to 15, 15 to 20. That's the histogram definition. Naive estimator states that I'm giving the logic behind it. Well, how do you know 0 to 5 is a good split? Why do you split from 5? We should have a continuous interval, basically. We should take the center of the interval and see how many goes into that area. So that has a sliding window, naive estimate. Okay? So the denominator is the same in this case. The numerator is changing. So in this one, there is something called k nearest neighbor estimator. In the previous cases, denominator was fixed. Now we fix numerator. We fix the numerator. Numerator is 5, right? Let's say k, number of k nearest neighbors. It is k. Now, in the denominator, you look at, you have 2 times n times the distance to the k closest neighbor. So, if you want to put this logically, for your data you pick one data, to cover k neighbors, how much area should you look into? So that tells you about the density about that area. For example, just to understand how it looks like, I put X here. For example, I find the 5 neighbors here, right? Okay. So the 5th closest one is this one as an example. So you have a relatively dense area. You can measure it because in the denominator you have the distance to the kth neighbor. Okay. But if the neighbors are something like this, okay, whenever you look at this, so look at the closest or kth neighbor. Kth distance is a little bit far. So based on this, you can also say that this is not a dense area. This is non-dense because if you look at the 5th neighbor, it is a little bit far. Okay, so this is another way to measure the density. The distance goes here. So if the distance increases, the density will go down. Okay, that is how it is measured. So this is a distance density estimator, k nearest estimator. So in this one, k is fixed. K is fixed. You look at where denominator you need to compute the distance to k neighbor, and it's going to tell you the density of that area. Yes.
So we are trying to estimate the number of neighbors.
So these are called density estimators. Okay, these are called density estimators. We are not trying to find the number of neighbors. That's not the goal. For example, the purpose is similar to the histogram. You remember what histogram is, right? It gives a distribution of data basically, but it has limitation. Limitation is you fix the intervals. Okay. The second naive estimator, what it does is, well, you don't need to fix the interval. You need to fix. You have the window size is the same, but you have a sliding window. Okay. This one is basically the difference is why do we work with intervals? Okay, that's the question. Let's look into the kth neighbor. Okay, so if kth neighbor is far or close, it's going to give us the density of that area. So we can have density estimator in that way. I don't know whether I have a also. Yeah. So this is the one example how it looks like. So if you look at don't look at the bottom, the numbers, okay? Just look at the graph. So when I say that the dense area in this one for K0 is this region. Okay, this is the most dense area. I can compute it. Okay, by looking at here, it's the most dense area for k is equal to 5. This is for k is equal to 3. This is the most dense area. There's also some density here. Okay. For k is equal to 1, there is going to be time where distance preset is 0, so it's going to go infinite. Okay. Maybe it's not good one to try out, but you are going to see where the data is appearing actually. This location, this location, this location, this location. But this is another estimator. Okay.
So,
yeah.
How would the area and density be defined in that? So with histogram we have interval.
Yes.
So with this one,
how do you determine it, right? So just look at first the data. Okay, let's look at the data. Okay, you see the data is here, 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 here. When you look at this data, by intuition, there are several places where data is dense. This location, okay. Dense, the data appear next to each other. Another maybe it's somewhat dense, but not too much. There is some gap. And maybe sometimes here, 2 is located here, 2 is close, but 1 is a little bit far. So there are 3 places I can, by looking at this, just observe by observing. I can state that, right? By observing. But how do I put it into formula? And how do I put it into formula? What I do is, for each point like this, okay, I try to find the fifth closest neighbor. The fifth closest neighbor, distance to the fifth closest neighbor gives me some idea about the density. If the fifth neighbor is very far, it means that I am not in a dense area. If the fifth neighbor is close to me, then I am in a dense area. That's the way it is done. Okay? This is the way. Yeah.
So the fifth neighbor you mean, are they going to be like in kind of order?
You sort them and find the fifth neighbor. Yes.
Okay,
neighbor.
we sort all those distance.
Distances and find the fifth neighbor. Yes. And then look at the distance for this position. So for number one position, what is the fifth neighbor? For example, it is this one. Okay. For example, it's the fifth one. This one. Then this is the formula. So you put it here. K is fixed. So this is a varying number, and then that's how you measure the density. I'm going to cover this concept later. Maybe. Okay. Any questions? There is also, let me mention this. In nearest neighbor, you already did it in the assignment, right? You submitted, hopefully. The problem is generating that similarity distance matrix could be too huge. You are measuring everything, okay? You are computing distance to everything. There's condensed nearest neighbor method. It does sampling of the data, okay? So what it does with the sampling is, I'm going to explain maybe in this way. So you see that all the data points that goes into this region, they are all positive. Okay? Maybe you don't need to check every point from that area, because whatever goes into that area is always positive. You just need to pick maybe one point, representative point from there. Then you could have a less dense representation, sampling of the data. Rather than maybe comparing with 50,000 data, you can just compare with 1,000 data if you do proper sampling. Because there are regions in 2D like this, they are all positive or they are all negative. Just pick something, one representative data. So what it does is, this is a selection method. You find the closest X prime, basically, you find the closest one, and you check the class of it. Okay, you check the class. If the closest data is different, then you definitely keep it. But if they are the same, then you are in the same, you are brothers, sisters, basically. You don't need to pick, different. Again, another representation from that one, because you are all the same, basically. Okay, that's condensed neighbor. So this is the method to reduce the size of the number of comparisons to the nearest neighbors. Yes.
So you take a sample from for example, the label is 0, you take the sample from the label 0, and then you compare the new point to that one.
Say again one more time.
So let's say we have 25,000 data sets with label 0. So you take a sample out of that zeros only?
It doesn't work like that. So what you do is, if you think it in terms of algorithmic way, you look at the first data, okay? Find the closest neighbor. If it is the same as the closest neighbor, you don't pick the closest neighbor in your data set. Okay, you skip that one. Then you continue with the second row in your data set. Again, you find the closest neighbor. If it is the same as the second row again, the closest neighbor, you don't pick it up. Okay, you eliminate it or you pick the data. That's the way it works.
On that, assume for this last data set we use, most of the like zeros are always like together. Like first, like let me say first 50 zeros or something.
But they are not ordered based on their similarities, right? They are ordered based on the classes, but they are not on the similarity.
So we have to order them based on similarity before checking out.
I mean, what you do is like you build, for this condensed neighbor, it's a type of sampling method. Once you build that distance matrix, you can analyze whether the closest one is in the same class or not, and then you decide whether to pick the closest neighbor in the new sample.
So this is done on the second iteration, not on the first one.
Let me put it this way, just to be clear. This is the step that you do before starting KNN. Okay, this is a sampling method. Okay, but how do you do sampling? You don't do sampling randomly. What you do is you need to know if data is measured in a positive. You just need one sample from that area. You don't need all the samples from that area. How do you determine that? You can use an algorithm like this to determine whether the closed data is positive or not. So this is the sampling method. Once you generate this sample, let's say originally it's 25,000, maybe you get 5,000 after this process, and then you use that 5,000 for KNN algorithm.
Training set.
It becomes your training set.
See, Z does not change.
What is it?
I'm trying to read until Z does not change.
So what it means is you find the new closest data. Okay, you go continue next item. You add it to Z, right? You continue with everything. Firstly, you try for all X. Okay, you go through all X in random model. So you find the closest.
Well, X is the set of data points. So the big data. What is X? Like
X is your original data. What's the original data? So you add data after processing each data point. Okay, you go through all of them and then you update Z. After a while, Z will not change. It will not change because you look at the closest data point and you are done with it. You either pick it or you don't pick it. And then Z will not change.
class means whether or not it is in Z.
What is it?
Class of X, like the function class.
Yes.
That means whether or not it's already in Z.
Repeat.
Class X
Yes.
not equals to class X prime.
Yes.
This is the condition to show that X prime.
So you look at the closest data item. The closest data item is a different class. So this data is unique. Okay. So it is different from its closest data point. So you add X to Z.
Does that mean we are comparing the label of that class, like that observation X?
Of course, you compare. You compare. What you do is this is data 1, data 2, data 3, data 4, etc. This is positive, negative, negative, and then negative. You find the closest data for this one. An example, this is positive. Okay, ignore it. Don't take it. You look at this one. The closest one is KN closest. This is negative. Don't pick it up. For this one, the closest one is negative. Pick it up. For this one, it is positive. Closest one is positive. Pick it up. For this one, it is negative. Don't pick it up. So for each data, you decide whether you need to put it into your new sample or not. So I think the problem comes this one. Okay, so sometimes when solution is provided to you directly, it may not make sense. But think about this one. Okay, how do you know you need to pick? It's a region of all positives. How do you know you need to pick that point or not? How do you know in your new sample? I said that This area is all positives. I don't need all the samples from here. Maybe I just need one sample from this region. How do you make that decision? How do you come up with that algorithm?
At random.
From the whole data set?
No, from that region.
How do you know that region? Something. How? No, you cannot do sampling. How do you know that region?
Through the labels, right? Through the class or
No, this is not plotted, right? If you see the plot right now, it's not plotted. How do you know it? What you do is, this is what algorithm says, find the closest data point for this one. Find the closest. Closest is this one, let's say. Okay? Closest is this one. Okay, these are in the same class. Then I don't need to take this one.
Why?
Because I know that it's now positive region. That's how do I identify I am in a positive region or not. How do I determine I am in a negative region? I look at my neighbor. Okay? If we are in the same class, we are in the same room, we just need one person. But if you try to solve this problem by yourself, if I don't give the algorithm, if you think of your solution, you're going to come up with something like this.
X prime.
Yeah.
what you say is about the dropping and accepting that you're doing there. So the first one you're picking is just like plus.
Look, my data is plus. I look at the closest data, it's plus 2. So I don't pick a D1. Because they are the same. So I am the same as my neighbor. So I am in a dense area. I don't need to pick that one. The second one is D2. Okay. I look at the closest one. Closest one is mine is negative. The other one is negative. So still we are the same. So I don't pick D2 as well. Okay. I could do with D3. D3 is positive, but my closest is negative. I am not in a dense positive area. So I need to pick that one.
But it's positive. It's having the negative.
My closest neighbor is negative. I am not in a region that are all positive. That's what it means. Yeah.
Then when you get to the next one, you didn't choose negative again.
D4 is negative, but my close neighbor is positive. So I am not in a negative area. I am because my close neighbor is positive. So I should be very careful about that region because I have negatives and positives. So I picked that one too. Does it make sense?
We'll see.
Okay. Okay. I'm going to start a new topic. Bayesian decision theory. Hopefully it's going to be a little bit fun. The other one is learning problem is more theoretical, but this one is a little bit more applied. This is a probabilistic learning. So meaning we are going to compute probabilities. Probabilistically, we are going to get an answer. So that's the very common. Secondly, it's a very good properties, incremental learning. Okay. It's a very important property. So when you add more data to your training set, you don't need to rerun all your algorithm. That's what we mean by incremental. If you rerun all your algorithm with the same training set again from scratch, then it's not incremental. But if you just say that this is I found a new data and I want to add it to my training set, you just need to make a few operations and it's going to be done quickly. That's incremental. And there will be probabilistic predictions. So let's try to understand this. We have a data X whose class label is unknown. Okay? We don't know the class. Okay? We would like to find the probability of X belongs to class C. So this is will be called I'm going to put it this way. This is probability of X, the probability of observing X in the population. Okay. That's X data. Probability of C is a class. Okay. How frequently, what is the probability of observing that class in the population? And that is what it means. And there is a conditional probability. It is written this way, there's a separation. It's called conditional probability. Given B, we know that B is true. What is the probability of A? But we know that B is true. Okay. So for example, I tell you that it rained. Okay, it rained. What is the probability of grass is wet? I tell you it rained. It's a fact. Given that fact, you try to find the probability. If I just ask what's the probability of grass is wet, you need to consider all possible scenarios. Okay. It might have rained, it may not have rained, so you need to consider all possible scenarios. Okay. So these are important, but our goal is this. So it says that given X, so I give you this data. What is the probability that it belongs to class C? That's the way that we put into probabilistic notation. Given X, it's given. What is probability? What is probability that it belongs to? Okay. Probability C is prior probability of class C. Probability X is probability that sample data is observed. There is also this notation. So what does this mean? Probability given class C, we know that, let's say, the grass is wet, so we know that's a class. Okay, whether it's wet or not. What is the probability of observing X? This one is from the general population, and this is from the specific population. For example, X could be student. Okay, what is the probability that we observe student in the general population? Okay, let's say our class is biased computer. Okay, what is the probability that given that this person bought a computer, what is the probability that is a student? So I restrict my population now to that specific class. In that class, what is the probability that I observe that X? Does it make sense? Okay. So this is the core of Bayes classifier. Okay. So if you look at this problem, okay. So this is the general formula. Always. So you can write the formula. Probability given A, the probability of C can be written as P probability of A and C together, both of them are happening at the same time, divided by the given condition. Okay. So in the numerator you have the probability of happening them together, both. Okay. And then in the denominator you have the given condition, the probability of. So this is the formula for conditional probability. Okay. One point. This is the probability, conditional probability. This makes sense if you look at it. So what was the example I provided? Student buys computer, right? Buys. So I have to check the population of students in the numerator, in the denominator. These are students, the probability of being students. And in the denominator, I need to see how many of them, how many I have basically student and buys a computer. It's going to give me that probability. But this is a very reasonable thing. Okay. So this is the definition of conditional probability. This is just a definition. But my problem is, this is what I need to solve. This is my class. This is my. I can also use the second formula here. So look at this. In this case, given C, probability of A. Given C, probability of A. So I again have in the numerator together A and C. It doesn't matter. C and A and C are the same. They are together. Okay? Happening, both of them are happening together. There is no C and A and C are the same. In the numerator, I have the given condition, right? So you say that. So the critical part here now, I can determine this one. Okay, I can determine probability of A from the population. But how can I determine this one? That is my question. My question then, how do I solve it? I need to solve this one. I'm going to use the second formula here. What is the second formula? I can see that I can compute this by multiplying this probability of given C, probability of A times probability of C. You see that? From here, probability of A and C is multiplication of these two expressions. Then I can write in this way. I replace it, and given A, the probability of it belongs to C is probability of A given C times probability of C divided by probability of A. Does that make sense? No? Yes? In the future? It's not in the test, by the way. But you don't put yourself stress, okay? But did you understand how I derive this expression? So this is the core part. I'm going to give an example, but I will give an example, it's going to be better. And so this is just a repetition of the same things. So we have evidence of Px, it's the likelihood of X for class C, and it's a prior probability. Let's do this one as a starting point. So we know that meningitis causes stiff neck 50% of the time. Okay. The probability of, let me write this, given meningitis, having probability of having stiff neck is 0.5. I'm going to put it that way. Whenever a person has meningitis, it's a given fact, the probability that the person has a stiff neck is 0.5. And probability of a patient having meningitis is from the population is 1 over 50,000. Okay. That's given. And in the population, the probability of having stiff neck is 1 over 20. So when someone goes to a doctor, that person goes to the doctor with a symptom. The person does not go to the doctor, I have a meningitis, typically. Okay. So in this case, whenever someone goes to a doctor, he or she says that I have a stiff neck. And the doctor will consider the probability of whether this person might have meningitis or not. Does it make sense? The patient goes to the doctor with a symptom, stiff neck, and we want to know whether this person could have meningitis or not. Okay? Given this information. So this is the formula. This is the expression. Patient K tells us that he or she has a stiff neck. Now I need to find the probability of meningitis. You can write the formula we already provided. So you reorder the conditional probability type. Okay. Probability of given meningitis, probability of stiff neck given meningitis times probability of meningitis divided by probability of stiff neck. This is the formula I just provided a few minutes ago. This is the formula. It's the same formula. You need to memorize it. Okay. Then you put the values 0.5 times 1/50,000 divided by 1/20. You get 0.00002. Okay, don't panic. You may stiff neck doesn't mean that you have meningitis. It's very low problem. But stiff neck, may have many different causes, not the meningitis. Does it make sense? Now, the problem is, in the previous case, I had one attribute on one case, stiff neck, but real objects or the data that you work with has hundreds of features, like embeddings. This is 800, 1000 feature set, but what was that feature? No, that's the size of the data.
Yeah.
Embedding size. Number of embedding. What is it? 1000. Let's say 1000. Or take a person. Whenever we have a person data, typically we have demographics data like age, marital status, salary, education, etc. So we have multiple features. How do we solve if the data has multiple features, not single attribute like stiff neck? Okay, that's we have more than one feature. Okay, so we have a record like that. Now the question becomes then, okay, given those feature values, attribute values, okay, this is age is 30, this person is a student, and salary is 100K. Given this, how do I determine the class? It's not a single attribute value anymore. Now I have a set. I have a set of values or list of values. Okay. So there are some approaches, but the most typical solution for this one is called actually, if we write this one, let me expand it, write this one, the question becomes like this. Okay. So given all this process, if you write it in the same way, this is what we get. Okay. So this is the critical part. We don't know how to solve this part right. Given say I can find the probability of C, I can handle that, but I don't know how to solve this one. The solution is called the basic solution with strong assumption is to assume that attributes are independent, which is a very strong assumption and which is not typically true, but somehow it still gives good approximate results. For example, there is a relationship between age and student, being student. You cannot say that they are not related. I believe there is a relationship between age and salary. But you cannot say they are independent. But for simplicity, this assumes that they are independent. Okay, that's because we can have a solution for it. If it is independent, okay, you may write this as multiplication of probabilities. Given probability C, given class C, the probability of first attribute times given probability of probability of A2 given class, again probability of AN given class. So you just need to multiply all of them. You can check the probability of each attribute basically given that class. For example, you just check what is the probability of age is 30 given by computer. What is the probability of being a student given by computer? What is the probability of salary earning 100K that person by computer? And you multiply all those probabilities, and then you are going to get an approximation. So what you do is, this is the general formula. I'm going to put it this way. If you have two classes, you are going to write it this way. Probability of, I'm going to simplify C1 as a two classes. You want to know the probability for class 1. I'm going to put C1 times probability of C1 divided by probability of X. Okay, I'm assuming there are two classes. And you need to compute the probability of X for class 2, and probability of X, C2, given C2, probability of C2, and probability of X. Okay. Then you pick the class that has the higher probability. You pick the class that has higher probability. Okay. I'm going to give an example. Don't worry. But you know that you compute the probability for each class and pick the one that has a higher probability. Then that's how you define it. But there is something nice here. That you can add even one more class. If you have 3 classes, this is what you need to do. Okay, C3, X, probability of X, C3, probability of C3 divided by probability of X. One of the difficult parts in Bayesian probability is the probability of finding X in population. The probability of X in the population is not an easy problem if we have complex features. Okay, because that person might be unique. If you look at it, we are unique in many ways, and most likely it is 1/1000, 1/1,000,000. If you look at all feature combinations. But if you look at all these probabilities, P, first one, second one, the denominator is the same. You see that? I need to find the class that has the highest probability. Then I just need to look at the numerators. Okay. Look at the numerator. Since the denominators are the same, the class that has the highest probability will have the highest numerator. So I just need to focus on the numerator actually. Probability of observing that class times given the class observing that X. Okay, that's the way we are going to do it. Now this is the example. You need to understand this example. We have, let me move this a little bit down. So we have a data set like this. Our class is by a computer. A person is likely to buy a computer. Our features include attributes: age, income, student, credit rating. These are my features. I want to build a probabilistic model, Bayesian classifier, by looking at that data. That's my input data set. My training set. C1 is biased computer. C2 class 2 is biased computer no. And I would like to analyze this data. Age less than 30, equal 30. Income is medium. Student is yes. Credit rating is fair. Is this person likely to buy a computer or not? That's what we are going to compute. So I am repeating. We have a training set which has 4 attributes. Our class is biased computer. I would like to determine the class of a new sample progressively, whether this person is likely to buy a computer or not. Okay? So I am going into answer. So let's do like this. The main thing is we need to find. I'm going to go back here. Look at the numerator. What do we have? We need to find out first P, probability of CI, probability of that class. That's what we need to find out in the numerator. Secondly, the conditional part. Given class, the probability of observing X. These are the 2 things I should find out from my training set. First is the probability of class. The second one is, given the class, the probability of observing X. Right? That's what I'm going to do. So this is my data. Let me enlarge this. X less than 30, income, medium, student, yes, credit rating, etc. So let's also first do this. What is the probability of buys? My class, right? Class is buys. Let me put it this way. Class is buys. Whatever. Buys. Let me put it this way. And what is the probability of buys? Yes. Let me put it this way. The probability of buys no. These are my classes. What is the probability of buying a computer from this data set? What you need to do is, typically, you need to count how many yeses you have and how many data you have totally. You do what? You take the ratio. How many yeses do we have? You counted?
No. And so yes.
1, 2, 3, 4, 5, 6, 7, 8, 9.
Oh,
That is computer.
not really for student. No yes.
So I'm looking at just class,
Mhm.
right? And we are just looking at the we don't look at the attribute. I'm just looking at the general population. How likely people are buying computer? Okay, we have 9 over 14. For buys no, 5 over 14. Okay, this is the first one. So we are done with one aspect. So we have this information. Second is, for each class, I am going to observe the attributes, the probability of each attribute. Okay, what are the attributes I check? Let's check this one. Okay, for buys yes, buys computer yes. What is the probability of age less than 30? So what you do is you need to let me mark the yes is one from here. This is yes, 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 and then this is yes, 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 yes. Okay. How many of them are less than 30? The ones that I marked with red. How many? 2. How many yeses do we have altogether? 9. The probability will be 2 over 9. Did you get it? This is the beginning part, but you need to understand this because I'm going to repeat the same for a second again. Does it make sense? So there are, for students which I marked with reds here, these are my, not students, sorry. These are by computer. This is my class, yes. Yes, yes. So I checked it. How many of them less than 30? I see 1 here.
11.
2. The rows 9 and 11, right? That's very good. I have 2 out of 9. For no, plus no, buys no. What is the probability? I need to count the other ones. 1, 2 here. 3 here. This is row 8. And so on. So we have 3 rows no for plus no. What is the probability? 3 over?
14.
No.
5.
Just count the ones that don't buy. That don't buy. 3 over 5.
5.
So you just limit to given that class. That's a condition. This 3 over 5. Okay. 2 over 9, 3 over 5. You got that? What is the second attribute? Income medium. So you should do it the same thing for class yes. Should do it the same thing for class no. For each class, you need to find the probability of having medium income. That's what you should do. For buys yes. What is the how many mediums do we have? 1, 2, 3, 4. We have 4 medium, 4 classes. How many yeses do we have? Altogether 9. 4 over 9. It makes sense? So for no, let's do it for no, medium. Let's say nothing here. I see 1 here. 2. So we have 2 over 5 because we have 5 no's, 2 of them are medium. Does it make sense? Do the same thing for student? Yes. For each class. For yeses, I see 1 here, 2, 3, 4, 5. Have I made a mistake? Let's count one more time. 1, 2, 3, 4, 5. Have I made a mistake? Why do I have 6 here? Why it should be more like that? Do I made a mistake? The 7. 7 is also. So we have 1, 2, 3, 4, 5, 6. Here 6. And 1, 2, 1, 2, 3, 4, 5, 6. I have 6 students for class yes. So the probability is 6 over 9. For no, how many students do we have? No. 1. No, not that. I'm yeses. There's 1 here. Yes, there's 1. Plus no, student yes. And that's it. I have only 1 student for class no. Then it will be 1 over 5. You do it again for credit rating pair. I'm not going to count this time. You get 6 over 9, 2 over 5. Okay. Now, what you need to do is, you need to find this and that one for each class. So first, if you remember, this is what I'm doing. I'm going to go back. I am computing this first expression here. That's what I'm doing. And I am using multiplication of properties, naive Bayesian. That's why we plus naive Bayesian. So I multiply probability plus yes 0.222 times 0.444 times 0.667 times 0.667. I get 0.044. For the other one, I multiply 0.6 times 0.4 times 0.2 times 0.4. I get 0.028. For the numerator, I need to multiply with the probability of the class. I'm going to multiply this expression with the probability of this class. The probability of yes is right. Yeah, I think it's right. 0.0044 times 9 over 14. This will be 0.0019 times 5 over 14. At the end, these are the numbers. And we say that since the first value is higher than the second one, this person is likely to buy a computer. Make sense?
So for the EF given CI based on the formulas, can you flip it back the formulas?
Which one?
No, the first one before it.
Here? So what we did is we used naive Bayesian. Naive Bayesian is basically says that given each class, find the probability of attribute, and multiply the probabilities. So what I did here is, for class yes, I find the probability of age less than 30. For class yes, I find the probability of income medium income, and I find for class yes, I find the probability of being student, and for credit rating, I find the probability of being fair, and then multiply those 4 values.
Well, you choose this condition yourself, like you
This
want
one?
to base it on
This one. This is something that we want to know. It's like a test point, I want to determine whether this person is likely to buy or not. It's a very good question, by the way. We do not generate the probability tables for the data, test data. What you need to do is, in real life, because you need to do some pre-processing. For each value you see in the data set, you need to generate all probabilities. Age less than 30, find the probability. Age 31 to 40, compute the probability. Age greater than 40, compute the probability for both classes. For high income, compute the probability. For medium income, find the probabilities. For low income, find the probabilities. For student, no, find the probabilities. For student, yes, find the probabilities. And for credit rating, fair, excellent, find the probabilities. You look at the table first, compute all the probabilities. Then, whenever a new data comes to you, you just need to multiply the corresponding probabilities. I just do it in this way so that the idea is clear, but whenever you build the model is actually the set of those probabilities that is done for all possible values that appear in the data set.
So if it's gonna be X, maybe in exam, you're gonna set this X for us, so we don't have to like do for all of them.
Probably I'm going to give you an X, and you're just going to focus on some of the X. The test. Yeah. But in the assignment, you need to do the coding to compute all the probabilities.
All of them.
Yeah, but it's not you who is computing the probabilities, it's the computer. So you are safe.
It's just counting, right?
You just need to write the code. Does it make sense? Okay. Now, there is one problem, an important problem with this approach. This works very well for categorical data. What if your data is continuous? Age is like 21, 22, 31, 35, 37. Maybe it may still work because the age range of ages is limited. What is it is salary? You have all possible values for salaries, right? It goes up to 500,000. An example, it can start from, let's say, 1,000, go up to 500,000. Then the probability will be extremely low if you just look at that probability. How many people exactly have that exact salary in the population? It will be very low. We don't do it that way. What we do is we use
we pick range or something?
Something like that, but what we do is actually probabilistic distribution, the distribution of data. Okay, this is another example for this one. So you can annual income is continuous, others are categorical, homeowner is categorical, marital status is categorical, annual income is continuous. So you may need to assume that there is some distribution. Okay, this is the easiest way, and this is an acceptable solution to do it. For example, you may assume that annual income has a Bayesian distribution. You may assume.
Gaussian distribution.
Yes. And you have the normal distribution. Okay, normal distribution. So given that, if it is normal distribution, there are two things you need to find out: the mean and standard deviation. So this is becomes the formula. The formula looks complex. Don't worry about too much the first formula. Okay. You need to find out the mean, okay, of the average salary from data. You need to find the standard deviation from the salary. You need to find those. Then you need to given, for example, this is what you need to do. So let's say I need to compute this one. What is the probability of no, given the probability is no, what is the probability of income 120? Okay. So this is something that you want to find out. So you are given a data, it says that the person earns 120. what is the probability of observing 120? Okay. So this is the formula. Look at the formula here. Okay. We say that okay, it is 1 over, this is normal distribution, square root of 2 pi standard deviation. We already computed for now. 54.54. Okay. Then for the e to the power xi is 120 minus average. Okay, and 2 times the standard deviation. And then
What,
it's
what
going.
is, what is mu then?
Mu is average.
Oh,
Mu is average.
and sigma is
Sigma square is variance actually. So
Sigma variance, yes. Sorry. Yeah. Sigma is standard deviation. Sigma square is variance.
so we have the sample of the data, and then we have these age from 75 to 125. And we have the income from 75 to 125, and we try to what is no?
From the class.
Oh.
From the class. For that class, you need to analyze the distribution.
you need to see the like previous one.
First slide? Okay.
Yeah.
This is the previous
This
slide.
this
Oh, okay.
Well,
So you analyze the distribution for each class.
For the we want to find the probability of 120K salary for
As an example, for class 1, what is the probability of observing 120K for class 1?
that they're not borrower.
1 over 10, like 10%. For no, then no,
Okay.
then
So this is the problem, and that's the problem that we are trying to solve.
Yeah.
But if you look at the real data set, if it is a continuous value, and it could be even have some decimal points, okay? It's always going to be 1 over population, most likely.
Yeah.
If you have 100,000 people, maybe it's 1 over 100,000. But it doesn't give the real feeling of the distribution. So you need to assume that there is a distribution of data, and you need to look at that range where it is likely to happen. So you can look at an interval. Interval is very reasonable to look into, but the typical approach is to use a probability distribution. So where does the value appear in that distribution, and you can give a computer probability with respect to that distribution.
also so what
What we are doing is we are looking at the this is what we are doing.
we're trying to find the
Yeah.
probability distribution.
So
Normal distribution.
So this is our standard deviation. Let's see. The mean is 110. So if it is around here, it's going to be, so this our value is 120. So what we are doing is actually, we are not just looking at one value, we are looking at the surrounding of this one. So what is the area covered here with respect to the total area under that curve? That's what we are trying to measure actually. If it is very close to here, it's going a little bit higher. If it is very close to the somewhere here, the value will be very low. Probability will be very low. Closer to the middle, the higher the probability.
But so the formula is to calculate the
Calculate formula just gives this area with respect to the total area. But this is what it does. It's a normal distribution.
so
0.0072 is the area.
Something like this, a probability of observing that value. Yeah.
So what is the interval in this point?
Interval is, it is like this. Look at this. Epsilon. Okay, this is the interval. Observing that value in that interval. It's a very small value. That's the way we look.
So even for the small value, we can still find 0.0072.
If it is close to the, this is somewhat close to the mean, but this is a little bit high value. Because the value that I'm checking is 120, average is 110. You see that, right? This is close to the mean. But this is the formula, I mean, you just need to use this formula for continuous attributes.
That's
And
really
to be able to use it, you need to find the mean, variance, standard deviation.
That's only when the data is distributed normally. What if it's another distribution? Or in this class, it's just going to be normal distribution?
Yeah, it makes a normal distribution.
Okay.
It works fine generally.
Yeah, I'm just saying if the data seems to be a skewed one, we still,
Then it's not going to work.
yeah, that means you surely give us a data that is like normal.
Yeah.
Okay.
You need to analyze the data. I mean, otherwise, we analyze the data distribution, understand
Understand the one to use.
what it looks like, and then come up with the proper distribution. But usually, we go with normal distribution. Oh, it's already over time.
Really?
Don't. You are very good students, I mean. You always want to stay after class, I mean, but I posted a third assignment. Just, I want to mention what it is so that you are aware of, okay? Because you are going to have an exam, then I will go over the exam, then you are going to have presentations. So I'm not going to be able to cover this. So this assignment is almost the same as the second one. I believe you generated embeddings and stored them. You don't need to regenerate the embeddings. We have not done that?
Mm-mm.
If it is in your Jupyter notebook, if you have done it.
Yeah.
Okay. So you are going to use the same thing, but you are going to apply Bayesian classifier. That's it. Same problem with Bayesian classifier.
Oh, nine. The one we just did now,
Yes.
like the condensed.
And then not nearest neighbor. It's Bayesian.
The one that we are.
Probabilistic one. The probabilistic one.
This is the same data, but you will do the.
Same data,
But the algorithm is different. Like
yeah, a different method. Okay. There is one caveat in this one. I want to use at the end two-fold cross-validation. Okay, that's the difference. What is two-fold cross-validation? Normally you have training set applied test set, right? This is the way you do it. What to do is you reverse the test and training and then apply again the same idea and then get a good overview of the how Bayesian works. But for you, if I were you, what I will do is, okay, this is for learning purposes, what cross-validation is. I will try with the same percentage as KNN, like 70%, 80%, 90%, and try to determine how it compares with KNN. Okay? I will do it personally, if I were you. Once we do it, you don't need to do, cross-fold validation for that purpose, but to see if you use 90%, how does Bayesian work compared to KNN? Because you already have the results for KNN. This is right now, the date is October 25th. So I believe it is doable, but if you need additional time, let me know. All right, thank you very much.
How large would the data
The same data.
Same
Same
data.
IMDb.
Same.
But we're not using everything, but I don't think anybody.
I can't run everything.
use everything.
It's like it's not possible.
No, I think you can.
Okay, do your best.
I
Like,
live there.
so highest is 25,000.
I know, I use 50,000.
How many? You got 50,000? Okay.
How long does that take to
How-
run? It took a. I ran it
You
for
did
3 hours
25,
and I couldn't get
You
it.
did
25,000.
You did
25,000?
You did 15? Okay, we'll be in your next class. We'll be in your next class.
Oh, I ran it. Use the server.